Hello all. In this lecture, we'll have a brief discussion about what is linear vector space. Before we go into the case of general linear vector spaces, let's just talk about the n-dimensional Euclidean space. We've learned about vectors and we know that an ordered triple of numbers, say a1, a2, a3, if we are marking it in three-dimensional Euclidean space, it can either represent a point in space, or we can also tell that it represents a vector, and these numbers, this ordered triple of numbers, are the components of the vector along the coordinate axis. Now, uh, when we consider space of higher dimensions, we need more such numbers to represent a point or a vector in space. And if we are extending this to the n-dimensional space, where n is a positive integer, then we need an ordered n tuple of numbers to represent a generalized vector in n-dimensional Euclidean space. And we'll be just going through the various properties that vectors satisfy in n-dimensional Euclidean space, many of which are we know about them in the two-dimensional space or three-dimensional space. We are familiar with various properties of vectors. We have just extended most of the properties to the n-dimensional Euclidean space. Now, when do we say that two vectors are equal? We say that when each component is equal to the corresponding component of the second vector, isn't it? That is, u1 should be equal to v1, u2 should be equal to v2, and this should be true for all the n members in this ordered n tuple, and each one should be equal to the corresponding member in the second ordered n tuple of numbers. That is, ui should be equal to vi, where I goes from 1 to n. Now, how do we define the sum of two vectors? We add each corresponding component, isn't it? This is true for the n tuple also. u1 plus v1, u2 plus v2, etc. un plus vn would give me the sum of the two vectors u and v. And if we have a scalar k, then scalar multiple of u, k times u, is given by this n tuple. This is the same as we know about vectors. Suppose you are multiplying a given vector a1, a2, a3 with some particular scalar k. What do? We just multiply the scalar with each of these components. The same is the case when you consider the n-dimensional Euclidean space. Now, we have negative vectors also in n-dimensional Euclidean space, where if u is given by the components u1, u2, etc., un, then minus u would be given by minus u1, minus u2, etc., minus un. And just as we say in the case of, say, three-dimensional space, when you subtract two vectors, what you actually do is you add v plus minus u. The same is the case with n-dimensional space. And here also you can define a null vector, and a null vector would be an ordered n tuple of zeros. Now, the addition and scalar multiplication of vectors in En have the following arithmetic properties. U plus v is v plus u plus v plus w is u plus v plus w. So, addition is commutative, it is associative, and you add a null vector to any vector in En, you get the same vector. And when you're considering multiplication with scalars, this is true. And A times u plus v would be au plus av, and a plus b times u would give you au plus bu. So it is distributive. This property we call it distributive. So here you can see that we have denoted vectors in bold-faced letters, and a and b that have been considered here are scalars. And now in the three-dimensional space we define inner product like this, right? A dot b would be ab cos theta, or an equivalent expression in terms of components would be a1 b1 plus a2 b2 plus a3 b3. But in the n-dimensional Euclidean space, we define inner product like this. When you have u as an n tuple of u1, u2, etc. un, and v is an n tuple of v1, v2, etc. vn, then the dot product or inner product in a general n-dimensional Euclidean space is defined like this. It is u1 star v1 plus u2 star v2 plus etc. u dot v or the inner product is defined like this, where the asterisk mark denotes complex conjugation. And in an inner product, the first factor that we write, it is called prefactor, and the second factor is generally referred to as post factor. And as per definition, the inner product is linear with respect to the post factor and antilinear with respect to the prefactor. And that is what we have depicted here. What do you mean by linear with respect to post factor and antilinear with respect to prefactor? Suppose you are taking the dot product or inner product of two vectors. One is u and the other is a linear combination of v and w in this fashion. So you see that there are scalars associated with the post factors involved in the inner product, and this would be written like this: a times u dot v plus b times u dot w. Whereas if the scalars were associated with the prefactors and we have a dot product or inner product like this, au plus bv dot w, then this would be like this: a star u dot v, u dot w, and b star u dot w. See, here there is a mistake. Please read this as u dot w. Okay. So when you have a scalar associated with the prefactor, then it has to undergo complex conjugation and then you write the scalar product. But whereas if the scalars are associated with the post factor, you just need multiply the scalar product with the scalar. No need of taking complex conjugate of the scalars. This is what we call linear with respect to post factor and antilinear with respect to prefactor. And inner product also satisfies the following features. U dot v is v dot u star, and u dot av plus bw is a times u dot v plus b times u dot w. This property also can be added here. The antilinearity with respect to the prefactor, that also can be added here. And inner product of a vector with itself, that would always be greater than or equal to greater than 0, and it will be equal to 0 only if and only if the vectors themselves are 0. Okay, so you can write the condition like this: greater than or equal to 0 but it becomes 0 only if u is a null vector. Okay. Now we spoke about Euclidean spaces in general. Now let's see uh, what is a general linear vector space. Till now we were talking about the ordinary vectors which we represent with directed line segments. But now we are going to speak about a set of objects obeying certain axioms, just like the vectors in Euclidean space, and we are going to call these objects vectors. Even though we are calling these objects vectors, they are not just the ordinary vectors which we represented with boldface letters in the previous slide. These are not the ordinary vectors in the real sense. In linear vector spaces, we are going to talk about a set of objects. These can be our vectors, these can be matrices, these can be functions, these can be any set of objects, but these objects should conform with a set of axioms. And if they comply with certain axioms, then they are said to form a linear vector space. Now, before we go into the axioms that are to be satisfied by objects, if they are to form a linear vector space, we will just see how vectors are represented. General vectors are represented, not the ordinary vectors which we represent with either boldface letters or with a letter with an arrow on top. That is how we used to represent vectors. But here we are going to talk about certain objects which we call vectors. As I said before, these objects can be anything. It can be vectors, it can be matrices, it can be functions. So all these general vectors, we are going to represent it with this symbol. Okay, and this was a notation that was introduced by Dirac. You will be coming across such notation in quantum mechanics, Dirac notation for state vectors, and this is how he used the notation to represent the state of a system. And we will be using this same notation here also. Dirac called these vectors ket vectors, and the conjugates of ket vectors are denoted by this symbol, and they are called the bra vectors. And for simplicity, we will be just telling these are vectors and these are conjugate vectors. You will be knowing more about the bracket notation as you take your course in quantum mechanics. But as of now, we will just stick on to this notation for vectors. And we'll just define two basic operations, addition and multiplication by scalars. By addition, we mean that a rule is there for forming a sum, and that is denoted by psi 1 plus psi 2. For any pair of psi 1 and psi 2, if they can be added by such a rule to obtain a sum, then this operation is called addition of two vectors. Now, by scalar multiplication, we just mean that if you take a particular psi and you multiply it with some scalar, you get a new vector called k psi. So these are two operations which we define, which we require as we progress with the discussion of linear vector spaces. Now, let's proceed to the concept of vector space. An arbitrary set of objects, say 1, 2, 3, 4, etc., phi, psi, etc., form a linear vector space Vn if these objects, which we call vectors, meet the following axioms or properties. Okay, so what are those axioms? Let's see one by one. If phi and psi are objects in Vn and k is a scalar, then phi plus psi as well as k times phi are in Vn. This feature is called closure. I'll explain it a bit. If you are considering two objects in the vector space, when you add those objects, you are getting a new object, and that new object is also a member of Vn. Similarly, you are taking a vector, you are multiplying it with a scalar, and you are getting a new vector. If that new vector is also a member of Vn, then we say that the vector space is closed under addition as well as multiplication with a scalar. What do we mean by closed under these two operations? What we intend to say is when you are performing these operations, that is addition and multiplication with a scalar, you are getting new objects which are also a member of Vn. So by performing these two operations, you can arrive at all members in Vn, starting with say phi and psi. Okay, such a property is called closure. Now the second property, just as we saw in the case of our ordinary vectors, phi plus psi is psi plus phi. Addition is commutative. Similarly, addition is associative. I needn't explain it again here. Just the differences we have denoted here the general vectors, not our ordinary vectors. And scalar multiplication is distributive. This also we saw before. Scalar multiplication is distributive in scalars. So these two, all these properties are the same for vectors belonging to general linear vector space. We saw these properties before in the case of n-dimensional Euclidean space too. Scalar multiplication is associative. Here also you have a null vector such that you add null vector to some other vector, you get the same vector, and this is true for all phi's in Vn. Similarly, for every vector phi, there exists an additive inverse minus phi such that you add them up and you obtain the null vector. So, any set of objects are said to form a linear vector space if they comply with all these axioms. Okay. The set of numbers a, b, etc., which are used in scalar multiplication of vectors, they are called the field over which the vector field is defined. They are called the scalar field over which the vector field is defined. Now, if the field consists of real numbers, then we have a real vector field, and if they are complex, we have a complex field. See, the vectors are neither real nor complex, or actually we don't know what the nature of vectors is because we have not specified what our vectors are. Vectors can be anything. Just as I said before, it can be matrices too, it can be functions, can be any set of objects. All they need to do is they have to comply with all these axioms if they are to form a linear vector space. So, if you consider, say, the three-dimensional space of position vectors, it's an example of vector space over the field of real numbers. Similarly, if you are talking about, say, matrices, you can say that, say, 2 by 2 matrices, a set of all 2 by 2 matrices, they are, that's a linear vector space. You add one 2 by 2 matrix with another 2 by 2 matrix, again you get a 2 by 2 matrix. So the set of all 2 by 2 matrices, they can be called, they can form a linear vector space. So linear vector space needn't be ordinary vectors, they can be any set of objects. All they need to do is they need to comply with certain set of axioms which we discussed just before. I hope it was informative. Thank you.